This is the second video in a series that I'm creating to support a number theory course that I am teaching. And today we want to review the principle of mathematical induction. So likely, if you are at the level to take this course in the first place, then you've probably proved some things by induction. So this will hopefully be a review. So let's look at the standard setup for the principle of mathematical induction. So we want to let P of n be a statement depending on n. Then if the following two things are satisfied, then P of n is true for all natural numbers n. So let's dive into what these two things are. So first, P of 1 is true. So the statement where n is set equal to 1 is a true statement. So that's sometimes called the base case, because that really gets the whole induction argument off the ground. It's like the base for the induction argument. Next, we prove something called the induction step after making the induction hypothesis. And that says, for k bigger than or equal to 1, if P of k is true, then P of k plus 1 is true. So the assumption that P of k is true is sometimes called the induction hypothesis. And the fact that that leads to pk plus 1 being true is sometimes called the induction step. Okay, so like I said, if these two things are true for some statement depending on natural numbers, then that statement is always true. In other words, for all natural numbers, it holds. Okay, so now we're going to look at just a bunch of examples. So the first is the sum of the first n squares. And so that says that 1 squared plus 2 squared plus 3 squared all the way up to n squared is equal to n times n plus 1 times 2n plus 1 over 6. So let's do this by induction. So our base case will be the n equals 1 case. So I guess I should talk about what the statement is. The statement is that this equation is true. So we would say P of n would read something like 1 squared plus 2 squared all the way up to n squared equals this. So notice that's a mathematical statement that we can talk about it being true or false. Okay, so back to the proof. Our base case, n equals 1. So the left-hand side here is just 1 squared. But let's notice that 1 squared is the same thing as 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Well, that's pretty clear. We've got 1 times 2 times 3 over 6. That's just 1. So that means our base case is satisfied. Okay, now we're ready to move into the induction step. So let's suppose for some k bigger than or equal to 1, we have 1 squared plus all the way up to k squared is equal to k times k plus 1 times 2k plus 1 all over 6. So again, that's supposing that the kth statement is true for some arbitrary k. Then next, we want to prove that from this assumption, that the k plus first case also holds. So I like to use some terminology like consider the k plus first case or something like that. But here we'll just consider the left-hand side of the would-be k plus first case. So that'll be 1 plus 2 squared plus 3 squared all the way up to k squared plus k plus 1 squared. So again, that's the k plus first case. But what we really notice here is that these first k terms group together into our induction hypothesis. So that means we can apply the induction hypothesis to those first k terms. That's going to leave us with k times k plus 1 times 2k plus 1 all over 6. And then we have this leftover bit, which is k plus 1 quantity squared. So again, like I said, that's from the induction hypothesis. Now we're going to combine these things together, but we're going to do that maybe in what I would think is a clever way. So I'm going to take this and give it a denominator of 6 so it easily combines. That means I've got to give it a numerator of 6. Furthermore, we see that k plus 1 is a common factor between these two terms. This one has a single k plus 1 as a factor, and the other one has a k plus 1 squared as a factor. Okay, so factoring this out, we get k plus 1, and then what's left over is k times 2k plus 1 plus 6k plus 6 all over 6, where I took the opportunity to multiply this 6 through to the k plus 1 that was left over. Okay, so now let's see what's going on in this numerator. So we can multiply k and 2k to give us 2k squared. Then we have k times 1 is k plus 6k, so that's going to be plus 7k. And then we'll have plus 6. But hopefully that thing factors. So in the end, we're left with k plus 1. And then I want to notice that this guy factors like k plus 2 times 2k plus 3. So we've got k plus 2, 2k plus 3 all over 6. Let's check that. We get k squared, 4k plus 3k is 7k plus 6. Okay, so that's a good way to factor that. But notice that completes our argument. And that's because this k plus 2 is really the same thing as k plus 1, and that 2k plus 3 is the same thing as 2 times k plus 1 plus 1. So that means our formula holds with k plus 1 plugged in. So like I said, this finishes this proof by induction. Okay, let's clean this up and we're going to look at another. For our next example, we'll look at the alternating sum of the first n squares. So just to write this out, I want to notice that I start by having minus 1 to the n minus 1 times 1 squared plus minus 1 to the n minus 2 times 2 squared all the way up to minus 1 to the n minus n. Well, that's plus n squared. So like I said, I've got the alternating sum of the first n squares. So notice this guy and that guy have an opposite sign. And in fact, what we'll get is that that sums up to n times n plus 1 over 2, which you might be familiar with as a triangular number. So I actually just saw this identity for the first time, and I think it's pretty nice. Okay, so let's prove this like we did before by induction. So that means we need to start with our base case. So the base case will be the n equals 1 case. So in the n equals 1 case, we have the sum as m goes from 1 to 1 of minus 1 to the 1 minus m times m squared. So that's what this sum will collapse to if n is equal to 1. Okay, but let's notice that all we have to do is plug in m equals 1. That's going to give us minus 1 to the 1 minus 1 times 1 squared, which is 1. But next, 1 is the same thing as 1 times 1 plus 1 over 2, which holds this form up here. So it works out in this case. Okay, so now let's make our induction hypothesis and use that to prove our induction step. So let's suppose for some k bigger than or equal to 1, we have this statement is true for k. So in other words, the sum as m goes from 1 up to k of minus 1 to the k minus m times m squared is k times k plus 1 over 2. So that's like assuming pk is true. Now we want to look at the k plus first case. So we'll write that like this. Consider the k plus first sum. So this is going to look almost the same. It's just going to end at k plus 1, and it'll have a k plus 1 there. Okay, so let's write that out. So we've got this sum as m goes from 1 to k plus 1 of minus 1 to the k plus 1 minus m times m squared. Okay, so we want to maybe do a couple of things here. First, we'll strip out the k plus first term so that we will be left with a sum from 1 to k so that we can apply this. So notice taking out the k plus first term will give us minus 1 to the k plus 1 minus k plus 1. That's minus 1 to the 0, which is 0. And then k plus 1 squared. And then we'll be left with the sum as m goes from 1 to k of all of this stuff. So we'll have minus 1 to the k plus 1 minus m times m squared. But look, that sum that we have left over is not quite in the right form to use our induction hypothesis, but it really almost is. It's only away from the right form from a minus sign. Because notice we've got k plus 1 minus m in the exponent here. We have k minus m in the exponent here. So that means we can get rid of the plus 1, leave us with k minus m if we put a minus sign out here. Just think about distributing the minus 1 through. That would give us a k plus 1 in that exponent. But now that we have it like that, we can apply our induction hypothesis. So we'll be left with k plus 1 squared minus k times k plus 1 all over 2. Okay, now let's give these a common denominator. Notice we can take a 2 over 2 here, and then we can factor a k plus 1 out of this whole thing. And then after factoring, that's going to leave us with 2k plus 2 minus k all over 2. Okay, so that's from the 2 onto the k plus 1 that's left over after factoring out, and then we just factor the k plus 1 out of that term. But it's pretty easy to see that this is going to cancel down to k plus 2, which is exactly what we need it to cancel down for it to hold this formula up here. So that finishes this proof by induction. Okay, let's keep going. So our next example is about a sum of a finite geometric series. And that says for all x not equal to 1, 1 plus x squared all the way up to x to the n is equal to 1 minus x to the n plus 1 over 1 minus x. So there are a number of ways to prove this, but since we're on an induction section, we should probably do it that way. So starting with the base case, we have n equals 1. Well, I guess we could use n equals 0 as the base case. We get 1 equals 1 minus x over 1 minus x, which is 1, but maybe this is a little bit more satisfying. Okay, so n equals 1. Well, notice we have 1 plus x. That's going to be the same thing as 1 plus x times 1 minus x over 1 minus x, but that's the same thing as 1 minus x squared. I'll write that as 1 plus 1 over 1 minus x. So the formula holds for this base case. Now let's make an induction hypothesis. So we'll suppose for k bigger than or equal to 1, we have this kth statement true. So 1 plus x squared all the way up to x to the k is what we want it to be. So 1 minus x to the k plus 1 over 1 minus x. Now we'll consider the next case. So that next case will start on the left-hand side, and it'll be the sum up to x to the k plus 1. So we've got 1 plus x squared all the way up to x to the k plus x to the k plus 1. So here there's not much to do in terms of rewriting to use the induction hypothesis. We can just group those first k terms and immediately use the induction hypothesis. That's going to leave us with 1 minus x to the k plus 1 over 1 minus x plus x to the k plus 1. But now we can combine those fairly easily, giving them a common denominator. So we'll multiply by 1 minus x over 1 minus x. And if we do that, we notice that the x to the k plus 1 term cancels, and we're left with 1 minus x to the k plus 2 over 1 minus x, which is exactly what we need for it to hold this form. Okay, so now that we've looked at some basic examples, let's look at a couple of other objects that really lend themselves towards proof with induction. Okay, now we're going to look at 3 new objects that are really useful when studying mathematical induction. The first are binomial coefficients, then Fibonacci numbers, and then Lucas numbers. These are all actually kind of related to each other, and there are nice combinatorial identities between all of them. Okay, so binomial coefficients first. For integers n and k, such that n is bigger than or equal to k, which is bigger than or equal to 0, we have the binomial coefficient n choose k, that's how we read that, is equal to n factorial over k factorial times n minus k factorial. There are lots of ways to generalize this so that n is not an integer, or maybe even n is negative, but we're not going to talk about that right now. Okay, then Fibonacci numbers. So these are well known, maybe the most famous number sequence. So we'll define the 0th Fibonacci number to be 0, the first Fibonacci number to be 1, and then the n plus second Fibonacci number will be the n plus first plus the nth, and that's for all n bigger than or equal to 0. So that gives us the start of our sequence as 0, 1, 1. Then add the two previous, we get 2. Add the two previous, we get 3. The two previous, we get 5, 8, 13, 21, and so on and so forth. So that would be the first how many ever terms of the Fibonacci sequence. Now, Lucas numbers are similarly defined. We'll define L1 to be 1 and L2 to be 3. And then they have the same recursion as the Fibonacci sequence. So let's look at this. These guys look like 1, 3, then add those two, we get 4, add those two, we get 7, 11, add those two, we get 18, add those two, we get 29, and so on and so forth. So those are the first several Lucas numbers. Okay, so we want to prove a couple of results using induction about these three types of objects. The first of which is about binomial coefficients. And this is actually a different way to define binomial coefficients. You can just define the binomial coefficient n choose k as the coefficient of a to the k, b to the n minus k in the binomial expansion of a plus b to the n. But we're going to do it the other way, where we define it to be this number and show that it satisfies this rule. It's kind of like the same either way you look at it. Okay, so let's maybe jump into this. We want to start with the base case. So notice our base case will be n equals 1. But let's notice a plus b to the 1 is a plus b. But that's the same thing as 1 choose 0 times a plus 1 choose 1 times b. But then that's the same thing as this written in summation notation. Okay, so now let's make an induction hypothesis. So we've already used k as our index, so we'll use m as the tool for our induction hypothesis. So let's suppose for some m bigger than or equal to 1, we have a plus b to the m power is equal to this sum as k goes from 0 up to m of m choose k, a to the k, b to the m minus k. And then we want to consider the next object. So that next object will be a plus b to the m plus 1, which is equal to a plus b times a plus b to the m. Okay. But now we can apply our induction hypothesis to this second term to rewrite this as a plus b times that sum as k goes from 0 up to m of m choose k times a to the k, b to the m minus k. Now we'll distribute this sum onto each of those terms. So that's going to give us two sums. So we'll have the sum as k goes from 0 up to m of m choose k, a to the k plus 1, b to the m minus k. So let's just notice that that is taking this sum and multiplying it onto this a term. Okay, but then we're also going to need what we get when we multiply this onto the b term. So we'll have the sum as k goes from 0 up to m of m choose k, a to the k, b to the m minus k plus 1, like that. Now, we're running out of room, but I really want to make this clear. So let's maybe get rid of this bottom half, and we'll reintroduce the board just with this blue underline and then this blue grouping over here. Okay, we ended the last board with the expansion of a plus b to the m plus 1 as these two sums. Now we really want to dive into what we want to do to make this look like this general form up here. So we'd like to be able to replace all of the n's here with m plus 1s, and then we have finished this induction step. Well, let's see where we've done that replacement already. The only place is over here where we have m plus 1 minus k. I actually commuted the addition so that we could see that easily. That means there's a little bit of work to do to turn this from m to m plus 1. This, let's see, this and this. But we can do that by re-indexing this first sum, then pushing them together, and we'll see that we uncover a binomial coefficient identity. So let's re-index this so that we send k to k minus 1. Okay, so let's see what that will do. So if k turns into k minus 1, if k minus 1 is 0, k is equal to 1. And then that means this is going to go up to m plus 1. Because if k minus 1 is m, then k is m plus 1. Then furthermore, this is going to become k minus 1 in here. This k plus 1 is going to turn into just k plus 1 minus 1, or just k. Then finally, this k minus 1 in here will turn into m plus 1 minus k because of the distribution of minus signs. Okay, so now let's look at this. This and this are now like terms, except for this starts at 1 and ends at m plus 1. This starts at 0 and ends at m. So we're going to have to take the m plus first term out of this, and we're going to have to take the 0th term out of this, and then we can combine these. So let's see, the m plus first term will be m, choose m, and then a to the, let's see, m plus 1, and then b to the 0. So we'll just write it like that. Now the 0th term over here will be m, choose 0, b to the m plus 1. Okay. Let's see what we're left with in the middle. We've got this sum as k goes from 1 up to m of m choose k minus 1 plus m choose k, and then a to the k, b to the m plus 1 minus k, like that. Okay, great. But now we're essentially home free, so we can rewrite these using the definition. This is going to be m factorial over k minus 1 factorial times m minus k minus 1. So that's m plus 1 minus k factorial, like that. Then we're going to add that to m factorial over k factorial m minus k factorial. Okay, great. So now let's see, what does it take to give these a common denominator? Well, we're going to want to multiply this one by a k in the numerator and the denominator, right? To bring that k minus 1 factorial up to k factorial. Then we're going to multiply this one by m plus 1 minus k. So m plus 1 minus k. That's to bring this m minus k factorial up to m plus 1 minus k. So let's see what that leaves us with. We'll be left with m factorial times k plus m plus 1 minus k all over k factorial times m plus 1 minus k factorial. Okay, so that's by pushing all those together. But we're finally done, because notice that this k and this k cancels, and in the numerator we're left with m plus 1 factorial. But that means that this whole thing is m plus 1 choose k, which is exactly what we wanted it to be. So how would we finish this off? Well, we've just shown down here that this bit right here simplifies to m plus 1 choose k. And then we can push these back in. You might be worried about pushing those back in, but m choose m is the same thing as m plus 1 choose m plus 1. And that's because they're both equal to 1. And then finally, m choose 0 is the same thing as m plus 1 choose 0, again, because they're both equal to 1. So that means we can bring those back into this middle sum, and then it has the same form as this up here, just with n replaced with m plus 1, which is how we wanted to finish this by induction. Okay, so now let's do a couple involving Fibonacci and Lucas numbers. We're going to finish this video off by proving a couple of things regarding the Fibonacci and Lucas numbers using induction. So there are tons of nice identities involving these numbers. So there are tons of combinatorial identities involving these numbers. In fact, I have a whole playlist where I prove lots of Fibonacci identities if you're interested. But the two we'll look at relate the Lucas numbers and the Fibonacci numbers, and then involve the squares of the Fibonacci numbers. Okay, so let's look at this first one. We want to show that L sub n is f sub n minus 1 plus f sub n plus 1. Sometimes this is actually taken as the definition of the Lucas numbers. So let's maybe start with that one, and we're going to do a base case because we're using induction here. And in fact, I'm going to check two base cases just to show like how this works. So notice L1 is equal to 1 by definition, but that's equal to 0 plus 1, kind of by obvious arithmetic, but that's equal to f of 0 plus f of 2. So that means this formula holds in this first n equals 1 case. Let's check the n equals 2 case. So L2, that's 3 by our seed right here, but 3 is the same thing as 1 plus 2, sort of obviously, but that's equal to f of 1 plus f of 3. So the third Fibonacci number is 2, like we wrote right here. So this was the 0th Fibonacci number. We don't have a 0th Lucas number. Okay, so now let's make an induction hypothesis. So we'll suppose for some k bigger than or equal to 1, we have Lk is equal to fk minus 1 plus fk plus 1, and then we'll consider the next case. So that next case will be Lk plus 1. Now we'll use the reduction to write this in terms of the previous two L's. So this is Lk plus Lk minus 1. And now we can apply the induction hypothesis to each of these. So really what we're doing here is doing something called strong induction instead of induction. So those are equivalent, but just to carefully point that out, what we're really assuming is that Lm is equal to Fm minus 1 plus Fm plus 1 for all m between 1 and k. So we'll apply it to the kth case here and the k plus k minus first case here. So that's going to give us fk plus 1 plus fk minus 1 plus fk plus fk minus 2. So that's just how this guy expanded, and this guy expanded using our induction hypothesis. But now we'll combine these in a way that's advantageous. So let's combine this one with this one, and then this one with this one. So fk plus 1 plus fk is most definitely fk plus 2. And then fk minus 1 plus fk minus 2 is most definitely fk. But this final equation is exactly what we needed to prove this first statement by induction. Okay, so now let's jump into the second statement. Okay, so our second statement is that f1 squared plus f2 squared up to fn squared is equal to fn times fn plus 1. We're going to prove this by induction. So our base case will be that n equals 1 case. So that'll give us f1 squared, which is equal to 1 times 1. Well, it's really 1 squared. But that's the same thing as f1 times f2, given that they're both equal to 1. Okay, so now let's make an induction hypothesis. So suppose for some k bigger than or equal to 1, f1 squared plus all the way up to fk squared is equal to fk times fk plus 1. Okay, and now let's consider the next case. So our next case will be f1 squared plus all the way up to fk squared plus fk plus 1 squared. Then we visualize these first k terms being grouped together so that we can apply the induction hypothesis. So this is now fk plus 1 plus fk plus 1 quantity squared for this. Okay. But now we can factor in fk plus 1 out of this. That leaves us with fk plus fk plus 1. And then we can finish off by applying the Fibonacci recursion to have fk plus 1 times fk plus 2. But that's exactly what we needed to end with in order to prove this second statement via induction. Okay, well, let's get rid of this, and then I'll give you some warm-up problems for class. So now I'll leave you guys with some warm-up problems. So if you're just kind of watching this video for fun or to learn induction on your own, then these are good problems to start with to kind of get you off the ground, although you probably want to seek out lots more to practice. If you're in the course that I'm teaching, then make sure to have these written up to be put in your notebook at the beginning of class. Okay, so let's look at them. We've got 1 times 3 plus 2 times 4 plus 3 times 5 all the way up to n times n plus 2 is equal to n times n plus 1 times 2n plus 1 over 2n plus 7 over 6. So that's the first one to do. The second one is this nice inequality. 1 plus 1/4 plus 1/9 up to 1 over n squared is less than or equal to 2 minus 1 over n. And then finally, this nice sum involving binomial coefficients and Fibonacci numbers. Okay, so like I said, hand these in at the beginning of class, or if you're just doing this for fun, these are nice practice exercises. And that's a good place to stop.